Hello everyone, this is Adhish. I'm a grade 10 student from Mumbai. So today's problem is queries with bags, and the difficulty level of this problem is easy because it's a very straightforward application of the union find data structure. So in this problem we are basically given n bags and n magic cards which are manufactured by the union find disjoint data structure company. Each bag and card is assigned a number between 1 and n. Initially, the ith card is in the ith bag, and the manager wants to club some cards together. So there are three types of queries which you want to answer. The first type of query merges A and B into a single bag. The second type of query checks whether A and B are in the same bag. And the third type of query asks how many distinct bags are left so far. So since n q are up to 10 power of 5, we can use only one of the two heuristics for the union find data structure. We can use either path compression or small to large merging, which is basically union by rank or size. I'll be using both heuristics in the code, but in general, path compression and union by rank or by size, both are recommended. Since the values of n and q can be up to 10 power of 7 also, and even in that case, both the heuristics would be required. So let's take an example. Let's say we are given three elements in the set, and each element is initially in their own set, and we are given a second type of query. We are given 8 queries. In the first query, we need to perform a type 2 query where we need to check whether 1 and 2 are in the same connected component or not. So we'll print no because they are not in the same bag. In the second type of query, we need to find out how many distinct bags there are. So that's 3. In the first type of query, we merge them together. So there are 2 connected components now. Then in the next query, we check whether 1 and 2 are the same. They are the same because they just got merged before. Then we merge 2 and 3. So now there's only one connected component with all 3 bags. And we will print yes for any combination of bags because all of them are in the same connected component. So in general, we just need to implement this in a straightforward manner. So I'll explain briefly the idea behind the union find data structure, and then I'll show you the code. So the general idea behind the union find data structure is that for each bag I, you represent the leader of the ith connected component as pi. So initially pi is equal to I, and pi represents the leader of the ith bag or of the ith connected component, and we basically update the values of pi each time. So let's say we are merging two nodes u and v into the same connected component, or we are basically merging the two bags together. So in this case, we can simply merge the two bags together by setting the leader of u, by setting the parent of the leader of u to be the equal to the leader of v, where leader function will basically return us what is the leader of the ith connected component. Now in order to implement, so this is essentially like a one line merge method and a one line find method, or let's just name it find instead of leader. So a find method basically finds the leader of the connected component corresponding to the ith node. That's what find of I returns, or find of u returns. So in order to implement find of u, we could naively just keep on going to the parent. So actually this doesn't represent the leader. This actually represents the parent of node I. And if you keep traversing by going one parent at a time, you will finally reach the leader, and you will reach the leader when pi is equal to I. So when pi is equal to I, in that case I is the leader of the connected component, because when you perform the merge operation, this basically sets v to be the leader, and u is no longer the leader. That's why when you call find of u, you will go up to v and you will return v is the leader of the connected component in which u is. And that's why in the find method, when you call find of u, if the parent of u is equal to u, you will return u, because we know that u is the leader of the connected component corresponding to u. Otherwise, we will return find of the parent of u, because if you go from u to the parent of u, then you know that you'll keep going up the level one at a time, and you will finally reach the leader. And in this way we can perform the two operations naively, and this will pass subtask 1 for 30 points. In order to pass subtask 2, you can use two heuristics which are implemented to speed up the process of the union find data structure. So the first heuristic is to use path compression, which is the more commonly used heuristics. And path compression basically ensures that P of I not only represents the parent, it also represents the leader. So basically, when you find the leader to be V, you set the leader to be like V and U is the leader. But what you also do is that for all those nodes which had the leader as U initially, so let's say those nodes were X, Y, and Z. Let's say there were three nodes which had U as the leader initially, and you implemented this merge method. Then the key idea is that, let's say you call find on X and you want to find the leader. So that in that case, you replace the parent of X to be equal to U. So you don't let the parent of X to be U, you represent the parent of X as V. So basically you change the line of the code over here from just returning find of P of U to change it to return P of U is equal to find of P of U. So in this way, the parent of U no longer becomes the previous parent. So the parent of the node X, if you call find on X, then the parent of node X won't be U, it will be V. And this helps us because it reduces the distance which you need to traverse. So if you call find on X again, it will traverse only one length. And similarly, you can when you call find on Y, you replace the parent of Y to be equal to V instead of U, so that the next time you call it, you are essentially just doing an O of 1 operation. And in this way, that's path compression. This way you can compress the path essentially. That's why it's called path compression. And the second heuristic is union by size. This is actually not needed and I don't implement this in the code, but it's a useful thing to know. So basically, for each connected component, you represent the size of the connected component using size of U, and you will merge the two connected components together by merging the smaller connected component into the larger connected component. So in this case, if size of U is greater than size of V, you will not set V to be the leader, you will set U to be the leader. However, if size of V is greater, you will set V to be the leader, and you'll update the size of V accordingly. So you don't need to know that in too much detail because I'll not be explaining that. But you need to use path compression, and I'll show you the code which implements only path compression and will easily work for n and q up to 10 power of 6 even. You need to use union by size or rank if you want it to work for 10 power of 7 also. But in this case, it's only 10 power of 5. So that's why this will easily work in 1 second. And I'll show you the code now. So in the code, I use a struct UFDS to represent the union find data structure. Initially, I use vector int for the parents, and all parent of I is initially initialized to I, and the number of elements is given by n. Then for the first type of query, where we basically check whether the two nodes are in the same connected component, we will essentially just check whether find of u is equal to find of v. So if the leaders are the same, then we know that they are the same connected component, and this basically returns the leader. So this returns leader of the ith connected component of node I basically. And for checking whether two nodes are in the same connected component, you just need to check whether find of u is equal to find of v. For the second type of query where you merge them together, like this is actually a type 2 query, I think. used in type 2 query. Type 1 query is merging them together. So this is type 1 query, where you essentially just merge the two nodes together. And this is also used in type 3 query, because if u is not equal to v, so if u and v are not in the same connected component, so if they are in the same connected component, you will return away and you will not merge them. Otherwise, you just merge the connected components for u and v. So you will merge the two CCs, and you will set the parent of u to be v. And since the number of CCs have decreased by 1, when you merge the two nodes together, you will decrease num by 1. And in the end, for a type 3 query, you just need to print this num value. So in the main method, for each test case, for each query, if the test type is 1, we will merge the two together. If the query type is 2, we will essentially check if find of u is equal to find of v. And if it's a type 3 query, we will just print the number of connected components, which is given by ds.num, and ds represents the union find data structure. So that's what we use. And you can verify this code gets accepted, and I'll just submit this right away. So as you can see, my code got accepted. So I hope you like this problem and my solution. If you had any doubts in the union find data structure, do leave them in the comments down below. And if you like this video, don't forget to give it a thumbs up. Thank you.